If you've ever tried writing your own FFT algorithm from scratch, you might have found yourself staring into a wall of twiddle factors and recursion and wondering where to even begin. In this video, I'm going to walk you step by step through writing a clear, portable FFT implementation. No black boxes and no shortcuts. You'll not only see how the code works, but also why it works, and how the divide and conquer structure of the FFT actually plays out in practice. But why bother writing your own FFT algorithm? After all, plenty of libraries already exist. Why reinvent the wheel? The answer is a combination of education and innovation. Writing the algorithm yourself deepens your understanding of what's happening under the hood, transforming the FFT from a black box into a powerful, intuitive tool. It also gives you the flexibility to tailor the code to your specific environment, whether you're developing for embedded systems, optimizing for hardware constraints, or simply exploring the maths in your own way. We're going to code our FFT implementation in JavaScript. Why JavaScript? Because it runs in every browser, requires no setup, and lets you experiment with the code using just a basic text editor. I like the editor Notepad++, link in the lesson summary below, because it colours the syntax, making the code easier to read and debug. But any text editor will do. JavaScript is one of the most accessible ways to get hands-on. Don't worry if JavaScript is not your language of choice. You can port the code into Python, C++, or many other languages later on. We're deliberately avoiding language-specific libraries and doing everything explicitly, so the code stays clear and portable. I'll also link to some handy tools, again see the lesson summary below, to help you translate your code into other programming languages when you're ready. Before we begin, an important point. This first implementation we're going to build together is not the most efficient of implementations. Oh, it will work just fine, but there are ways of optimizing the code that only become clear after you fully understand how the algorithm works at a fundamental level. Even then, there's no single best way to make it faster. Efficiency often depends on the specific hardware or environment you're working with, as we'll discover. That's why in this video we'll focus on building clarity and confidence. Once you've seen the mechanics in action, you'll be in a great position to take what you've learned and explore different ways to refine your code for better performance. At the end of this video, I'll show you how you can continue that journey. So let's declare our FFT function. I'm going to call it myFFT, which accepts an array called samples as its input. It's important to note at the outset that samples is an array of complex numbers. But all the initial samples are real. How can we convert these real samples into a complex array? Easy. We just set the imaginary part to 0, like this. So the samples from the signal from the worksheet would look like this. Our first task is to repeatedly split the signal into even and odd samples. To do this, we'll write a function that calls itself recursively to perform the splitting. Each time it runs, it will divide the input array into two new arrays, one for the even index samples and one for the odd ones. We'll start by defining these two arrays and then call the function on each of them. I've set n to be the length of the input array. Since we're splitting it in half, each of the even and odd arrays will contain n over 2 samples. To make this clearer in the code, let's define a new parameter m to represent the length of the split arrays. So m is simply half of n. We'll be using both n and m frequently throughout the function. This is all very well, but the even and odd arrays contain no data. So after declaring them, we need a for loop to extract the even and odd samples from the input array before the recursive call. We're almost finished the splitting stage, but we still need to define a stopping condition for the recursion. Without it, the function would theoretically keep calling itself forever. In practice, of course, an array can't contain a fraction of an element, so to prevent runtime errors, we need to stop the recursion before the size of the array drops below 1. To make this code portable across different programming languages, including statically typed ones like C, I'll use n is less than or equal to 1 as the boundary condition to ensure that in such a case the function returns before we calculate m. This avoids the need to define m as a float, as when n equals 1, m will be 0.5. This keeps the logic simple and type-safe. It also ensures that we're always working with whole number array lengths, which is essential when managing indices and memory in lower level environments. Now, I could use n equals 1 as the boundary condition, and in this specific case it would work just fine. But n less than or equal to 1 is more robust, as it safely handles any unexpected or malformed input, such as an array length of 0, without allowing the function to continue into invalid operations. It's a small defensive step that makes the code more resilient and future-proof. So this is our basic divide function. However, I want to add 2 more things to this function. Firstly, to get a quick look at the results, I want to output the contents of the even and odd arrays using a console.log command. This will display the values in your browser's developer console, which you can open by pressing F12. The map function used in the console.log is simply there to extract and display the real parts of each complex number. Without it, the console would show each complex number as a collapsed object, which you'd need to expand manually to inspect. Since the imaginary parts are all 0 at this stage, focusing on the real values is sufficient for now. The second addition is to ensure the array of samples we start with contains a valid number of elements. Remember, we are repeatedly splitting the array in half. If the number of samples is not a power of 2, we may end up with empty subarrays. There are a number of ways of dealing with the problem, but for simplicity's sake, we'll just throw an error. So let's run the code and see how it divides the array. Here's the output. Notice the order in which the recursive function has run, which is interesting. Here's the first division. Here's the second. But look what happens. The function goes down one branch of the recursion tree, completely dividing the samples as much as it can, and only then returns up again to go down the second branch. This recursive approach, unlike the more intuitive step-by-step method we explored in the earlier animation, reveals something important about how the algorithm processes data. Instead of completing one full level of the splitting before moving on to the next, the function dives all the way down the rabbit hole, so to speak, reaching the smallest possible subarrays before working its way back up to combine them. This structure reflects the divide and conquer nature of the FFT, but it also introduces a key trade-off. While recursion makes the algorithm easier to write and understand, it comes at a cost. Each function call adds the overhead of having to store the context of the calling function, its variables, position in the code and return address, which can reduce the overall efficiency of the algorithm. We also have to over-divide, ending up with arrays containing a single element before climbing back up the tree and performing the 2-point DFTs. This final stage is unnecessary for the calculations, but necessary for the recursive nature of the algorithm. However, we've wasted a divide stage that we didn't need to do, just to satisfy the recursive structure. All of this gives us room for improvement. We'll discuss a more efficient approach in the next video. So now we've successfully divided the array, we need to conquer the problem. The beauty of divide and conquer is that to conquer a 2-point DFT is ridiculously easy. We just have to add the 2 samples for the first output and subtract them for the second. Let's add this to our FFT function. The first thing we need to do is set up an array to contain the results of the calculation and return that array to the calling function. This array will contain the combined result of the 2-point DFTs we're about to calculate and forms the combined part of the algorithm. Next, we need to loop through the array, calculating the 2-point DFT for each pair of samples. The order in which these results are stored in the results array is crucial because the results of each split must be combined in a specific sequence to preserve the integrity of the frequency components. An error in one combination will propagate through the process, affecting all the subsequent results, leading to an incorrect output. Therefore, the results must be placed in their correct positions, in opposite halves of the array, to ensure proper recombination during the later stages of the algorithm. Here's the first result, calculated by adding the two samples together, which is placed in the first half of the output array. And here's the second result, calculated by subtracting them, which is placed in the second half of the output array. But this code as it stands won't work. There are two reasons for this. The first is that the even and odd arrays contain complex numbers. Therefore, both the addition and subtraction need to be complex addition and complex subtraction. The second reason is that we've forgotten to multiply the odd samples by the appropriate twiddle factor. Let's first add the code to calculate the twiddle factor. Here's the real part of the twiddle factor, and here's the imaginary part. Now we need three helper functions, one to add the two samples, one to subtract them, and another to multiply the odd sample by the twiddle factor. I'm going to call these complex add, complex subtract, and complex multiply, and we'll call them in our code like this. So what do the three helper functions look like? To add two complex numbers a and b, we add the real and imaginary parts separately, like this. To subtract two complex numbers, we just subtract the real and imaginary parts separately, like this. Multiplying complex numbers is a bit more involved, requiring the FOIL method we used in the worksheet to expand the terms. We can easily replicate that method in code, like this. So our completed FFT function looks like this. If you'd like to download this code and use it as a basis for your own FFT implementation, then head over to the link in the description, where you'll be able to do just that. As I said in the introduction to this video, this code uses the recursive approach and will work just fine. It's compact and readable, but it's not the most efficient approach, and where the FFT is concerned, efficiency is the name of the game. There are many areas for improvement, ranging from software tweaks to taking advantage of various options that may be available to you in hardware. To help you optimize your own FFT implementation, I've put together an online course that this video is part of. It begins with a deep dive into the history and theory behind the FFT, not just the algorithm, but the thinking that led to it. My aim is to help you understand how these ideas evolved into the many different implementations we see today. In the video that follows this one in the course, I've gathered insights from a range of FFT professionals to explore specific ways you can make your code faster and better suited to your particular hardware or application. The first 4 videos from the course are available right here free of charge. Just click on the thumbnail to begin your journey and see how the FFT really works from the ground up.